So welcome to this course lecture on dynamical field theory. It will be focusing on detection decisions, but I'll also really lay the foundation. So we begin by briefly reminding you of what we did 2 weeks ago when we talked about neurodynamics for individual activation variables on neurons. So we recognize that their time courses are generated by a dynamic system here written down as an equation. It has this minus u term that's very characteristic that makes this negative slope, and that's really responsible for making attractors. For instance, here is an attractor at a particular level of activation that is dictated here by resting level h, a negative number, and input s, called s here in the figure. If you compute the fixed point of that, you say u dot equals 0, you put u to the other side, and you get u equals h plus s. So that will be this fixed point. So the minus u terms makes that a stable state, makes the negative slope, and it really brings about changes in time course. So if you have changing inputs, they move this negative minus u function up and down, and as a result, the attractors move left and right. So here, for instance, if you initially were in this attractor at the resting level h, that's negative, and you added a step function input, then the curve would be shifted up, the attractor moved to the right, and you're being attracted, exponentially to that new state. The neuron or activation variable would then pass on to other neurons only the sigmoided value, the thresholded value that goes to this threshold function that is called g here in this plot, and sometimes called sigma. So I think you're quite familiar with that after the exercise. And what we actually then discussed were these two simplest dynamical neural networks: a recurrent network of one neuron exciting itself, which has the detection instability, by stability and so on. We had a chance to study that a little bit. And a neural network consisting of two neurons that are inhibitorily coupled. So the sigmoided output of one inhibits the other and vice versa. And that's where we demonstrated selection. And what I'll do from now on is I'll show you, really work with these two mechanisms and show you how these two mechanisms find themselves in population of neurons that we call fields. And there they will be responsible for detection decisions, but also for much more general kind of go decisions, go, no go, onset of something. Ultimately, in the end of the course, you'll see responsible for sequences. And this will always be about selecting, decision-making, selecting among multiple possibilities. Always be these two common mechanisms do a lot of work. So I want to go to fields, and fields are really an idealization of neural networks, so with many units. And I think in one introductory lecture, I mentioned here this idea that you can think of neurons providing input to each other. So for instance, if you have certain neurons that are close to the sensory surface and they get some input from sensation, they would then couple to other neurons by providing their sigmoided output to those neurons, and you could cascade that, and thus you could create a forward neural network. And that, I'll come to that. That's related to what we just talked about in the neurophysics tutorial last week about tuning curves and feature extraction and so on. People sometimes call these ideas, talk about these sort of networks as doing something called space code, also called labeled line code, in the sense that the connectivity makes that a particular neuron, let's say here, this neuron here, is activated whenever a particular pattern of input is present. So for instance, if let's say S1 and S2 are activated, then this neuron is activated if these are all excitatory connections. And you could say sort of it stands for that, its activation is only sort of an index that whatever it stands for is currently present. So the activation is that kind of like a binary variable, if you wish. And what the neuron represents is determined by where it is in the neural network. This neuron stands for these two inputs, this neuron stands for those two inputs, and so on. This is a coding principle that has the German name Prinzip der äquivalenten Nervenenergien from the 19th century. Sort of an idea that if you have a particular neuron or particular part of the brain and you activate that brain, make the neurons there fire, or the electrical membrane potential become positive, then the perception or feeling or action associated with that is determined by which neurons these are, and not by how the activation came about. That's an old idea. So for instance, if you hit someone on the head, on the eye, let's say, and the visual nerve gets activated mechanically, you still see light. That's sort of a story here. I'm not sure how true that is. But there are actually really experiments that can probe that specifically. You can create hallucinations by activating certain kinds of areas. For instance, there's a famous experiment where in patients who are who have their brain exposed to electrodes because of some intervention to suppress epilepsy, and those patients sometimes you can do experiments with, and you can electrically activate little populations of their cortex, done to find out which area is where and make sure that you don't cut something really important. There are cases where people are able to create the impression of seeing something, certain shapes and faces and so on, by just activating populations. You know, there will be a direct reflection of such a coding principle. And again, code refers to how it maps to something outside when you describe the person. That's in contrast to the rate code idea that I presented in this Breitenberg lecture, which would be more appropriate for the periphery. And last week I showed you a little bit the neuromechanistic level for that, where sensor cells, for instance, transduce some physical thing into a firing rate or intra-membrane potential by a monotonic function. Here, an increasing function, you also look at decreasing functions. And then people talk about rate code in the sense that there is a one-to-one relationship between that physical thing and that neural thing that is sometimes a firing rate. That's why they say rate code. Now, in many neural networks, people will not really very strictly distinguish between these two kinds of principles, essentially mixing them more as arbitrary. And that is not entirely wrong, in that in the brain, you also find both aspects. So you find, for instance, that the rate of firing of neurons in particular areas might depend on some aspect of the stimulus. For instance, the rate of firing in the visual areas of the brain often co-varies with the contrast the stimulus has, and sometimes also with other features like the texture or second order contrast in some sense. Or, for instance, in motion perception, it might depend on the speed of the motion, firing less actually for faster stimuli. While in other respects, there is rate code, for instance, in the sense of receptive field that we talked about, that is, neurons will only fire to stimuli in a certain part of the visual array, or only stimuli that have certain properties like oriented and so on. And not necessarily modulating or modulating only very little bit, they're firing with the exact value along these dimensions. So it's a combination of both of these codes. So in dynamic field theory, we're idealizing and abstracting of these concepts, and we're talking about neural activation fields, and I come to the field aspect, but let's first say populations of neurons that are aligned here. The dimension is sort of a continuous index counting different neurons, and the meaning of those, or how they relate to things outside that model, outside the nervous system, is determined by their connectivity. Here is forward connectivity from the sensory surface. Let's say this is some sensory surface, could be the retina or the cochlea and so on. So the dimension would count maybe photoreceptors along the retinal surface, or some of these hair cells along the cochlea surface and so on. And so up here you would have some sensory signals, and they would induce activation in this population, and how would be dependent on the projections, on the synaptic pattern. So for instance, I'm assuming here that every sensor or region of the sensory surface provides input to a maybe somewhat spread out region in this field. So if you had a stimulus let's say you observe from one location in the field, then you would vary, let's say, the location of a little piece of light, or let's say more complex than cochlea. Let's think about light. Shine that light on slightly different locations on the retina, and you would find that this neuron responds most when you're shining that light here in this region and less here on the sides. And that would come from these forward connections, right? The light positioned as it is would make use of all three connections here, while light, maybe that's shifted such that this is no longer input from this location. That would only, make, less input, because these cables here already go to the neighboring neurons. So the tuning curve is sort of, you see, is the sort of inversion. This is a forward spread, and this is sort of the convergence, which is sort of the inverse, or you could say it's a dual picture of these forward connectivities. So if you have this connectivity to be quite regular, then you could say for every location in my field, I can say there is a region or location. You can characterize, let's say, the location by the maximum of this curve, a location in this input dimension that corresponds to that location. In a sense, stimuli at that location or with that feature value excite this location most. And so what we then would do, we would say that the pattern of activation induced here in this field approximates the input distribution by virtue of this forward connectivity. Someone comments that the slides are a little bit different. In fact, it's exactly these three slides that are changed. So I'll update that and you get these slides. So I just updated these slides. I had an earlier version on the website, but it's not very different. So in field theory, what we do is we neglect the discrete sampling of either space, of the sensory space and of that field dimension by discrete neurons. There are different historical perspectives on that. So neural fields actually were used as a mathematical approximation of cortical dynamics based on anatomical arguments, assuming that, and I pointed a little bit to that in the previous lecture, that in cortex along these surfaces, you have relatively homogeneous patterns of connectivity. These dendritic trees look the same if you move along the surface, and in fact they tend to overlap a lot, and therefore if you move an input pattern gradually along the surface, then the activity in the layer would also move gradually and look sort of the same wherever it is. And so then what they say, well, and then let's just have a smeared out version where we describe the neurons and the dendritic trees and so on by parameters, and then we would have only very few parameters. We would characterize the whole dendritic tree, maybe by its width and some feature that would be corresponding to having certain parameters that describe the, let's say, the width of this set of vectors here, of the spread. And thus we get rid of all these millions and millions of parameters of synapse to synapse discreteness. You will see later, and I'll make a separate little tutorial about that, that there's another view of this where it's actually a bit more abstract, where the continuous nature really comes from so-called population code, population representations, and it's something like a projection from one space to lower dimensional spaces, and it lies in the nature of that projection. It's sort of like the kernel trick. Some of you might know that in machine learning. It's a little bit more abstract reason for having continuous fields. Good. So that's sort of the sensory side of it. You could think that there would be a very analogous way of thinking about the motor side of things. So let's say you would have some peak in a field in some brain area, let's say motor cortex, and I'll show you examples of that later. And then you could say if they are connected in some way to the musculature in a systematic way, then maybe if I have a peak at a location that corresponds to a certain motor behavior, maybe a certain postural state or a certain movement state out in the periphery. And therefore you could say different locations in the field stand for different motor states. A bit ambivalent here about exactly what a motor state is. We'll have an opportunity to think about this more deeply in a couple of lectures down when we couple fields to actual agents, to Breitenberg-like agents. It's a little bit more complicated because in reality, there is never such a thing as reading out a peak. When you motor actually always amounts to ultimately some kind of behavioral dynamics, as I talked about in the Breitenberg lecture, which is why I plotted this here as a dynamical system, that the motor state rate of change is a function of motor state, and what the field does, erect an attractor for that state. And in reality, it's a bit more complex. It's not always just a fixed point. It could be like a moving state, could be like a limit cycle attractor and things like that. And there is actually neural substrate for doing that very minimally. The peripheral reflexes, like spinal reflexes, that characterize every muscle in the nervous system, they all are controlled by reflex loops that serve like peripheral control loops. They would make sure that something like that is true. But there could be also contributions from recurrent networks that don't necessarily just go through the spinal cord, that could go through the brain. So I will not elaborate on this much in this entire course. I will show you one example, a robotic example for the principle, but the motor part is discussed a little bit in my summer semester course. Okay, so summarizing, the concept that we'll be using from now on will be these activation patterns in fields of activation. So it's continuously many activation variables of the kind that we discussed so far that are defined over some dimensions, and we'll look at different dimensions. It will always look like, oh, this is the field over color or the field over movement or orientation and so on. But actually the meaning of these dimensions really comes from that forward connectivity, from ultimately some path through a complex neural architecture that comes ultimately from a sensory surface. So that would be the examples, visual auditory space, retinal, could be also allocentric, will actually get to coordinate transforms, how metric spaces like that can be transformed. It could also be features, so sensory surfaces, but then features like localized visual orientations, impedance, color, and so on. Or impedance would be a motor feature, sorry. And and actually for motor surfaces like the saccadic endpoint, which characterizes different saccadic eye movements or the direction of movement and so on. We'll get a few of these examples. We'll actually also be confronted with more abstract kind of dimensions like ordinal spaces and so on. I don't want to go deeply into that. So this is a little odd in a way. So we're writing down these fields, and the justification for them being about those dimensions comes from that connectivity within the architecture. And there's some kind of hidden assumption in these architectures that's consistent, that there aren't different sources of input that make the field sometimes be over color and sometimes be over, let's say, space. But that it's in terms of the forward connectivity, there's a unique path that really says uniquely what that field is about. And that is actually really another principle that we're postulating, and that does seem to be consistent with the brain. We sometimes call this the non-synesthesia principle. You might know that some people have some kind of abnormal feature that when a certain physical stimulus is presented to them, then they have a perception impression of along a different dimension that isn't contained in the stimulus, like hear something when they see a certain color, or that a certain smell links, they have a color percept associated with the smell and things like that. And so that would be theoretically, if we had a model of that, would be some kind of inconsistency where a field that stands for color in terms of its forward connectivity can also be excited sometimes by another forward path that should really then stand for something else. And so that is certainly exceptional in the nervous system, and so that hides a principle that these fields come about that way. So I will, it's always a little bit of a challenge for students to sort of wrap their head around this fact that these fields are about something and then forget where it really comes from. But ultimately, we'll develop over the course then an understanding of architectures, and it will be in these architectures that you can follow the path through the architecture to understand where things come from, where they go to. But it can be actually, this can actually be unraveled, can be grounded correctly, and I'm just hinting at that now. So if we for now ignore that, then the kinds of things that we'll be looking at will be these sort of things, like here's a perceptual field, and I'm just saying that field will be, let's say, defined over the horizontal position and the direction of a visual motion, let's say a point of light or contrast that moves in a particular direction. And you could span the space of possible movements through parameters. You could say the point could be anywhere in the visual array. That would be the horizontal and vertical position, and could have any movement direction, let's say. Then any motion state like that could be represented by a position here in this field. I've only plotted two, horizontal and position and motion direction, just because of the convenience of plotting. It would be in reality a three-dimensional field, so a blob in 3 dimensions. It's not so nice to visualize, so I just plotted two of those. So, space code principle, in the sense, the location in that space expresses what this is about, and then the activation is really just an indicator that is present. So a peak of activation, let's say at this motion direction and that horizontal position, would represent a particular motion stimulus out in the world, a particular state in the world. So I like to use this term sensory surface, and its actual meaning often don't really define that so clearly because it's a bit longer story, but its actual meaning is evident here. So you have a physical surface, like the retina is a physical surface, but there's also a more abstract kind of surface in a high dimensional space that has to do with the fact that visual stimuli aren't arbitrary. It's not true that you can take the retina and give input to just any receptor, and that would be a meaningful image. If you were to do that, and this input would be independent for every receptor, that would be sort of like a random dot picture, like a TV set that's not tuned, this flimmering snow that you saw there. So radiance levels or luminance levels vary from receptor side to receptor side randomly. That would be very high dimensional, but that's not what the world is like. In the world, there will be a lot of covariation in how the different sensors fire, and that comes from the fact that the visual array comes from surfaces that tend to be continuous with maybe one or a few light sources. So the amount of light reflected from a particular part of the surface varies continuously as you vary, let's say, your angle to that surface according to certain reflectance laws. There are maybe breaks, when the mapping on your retina now encounters a break in the visual surface, like an object ends and you see the background, but that would be sparse. In the scene there would be a few places like that, but most things would be correlated. And so in that sense, the state of possible stimuli, or actually not so much stimuli as possible states of the world that cause these kind of stimuli, would be much lower dimensional. And so here, this would be a very simplified example where if you think of a single localized movement, then a single localized movement spans a space that would be in this description 3-dimensional. And that is essentially the sensory surface, that state of possible, a space of possible physical causes of a sensory signal. So that's a slightly different idea, right, than just taking the sensory surface. This is not so stupid. When you look at motion, actually the sort of things that you perceive as motion are not that far from that. And you are actually not able to persistently see the motion of more than a small number of objects, maybe up to 4 that you can see simultaneously. Typically, when you see a moving object, you make a saccadic eye movement and then track that object, and then there's no motion on your retina. Actually, there's motion all across the retina. There's no object motion on the retina. This motion all across the retina, which is sometimes called optic flow, is actually not perceived as motion. This is often perceived just as ego motion. You feel yourself as an observer moving. So you're not seeing the stimulus, making some more abstract construct from that. So with respect to object motion, one, two, or maybe a small number of objects that are characterized by position and motion direction are actually good description. And so what I'm saying is there could be maybe up to 4 peaks, which turns out to be a magic number. We very often see that capacity limit of maybe 4 things that we can attend to at the same time, that we can remember at the same time, that we can make operations on at the same time. And you will see that it's very natural in these kind of fields. It doesn't have to be exactly 4, it could be 3 or 5, 7. And so the data for motion comes from so-called motion object tracking, where you're being shown a few objects, and then, for instance, the distractor objects also moving, and they're all moving then, and maybe look the same while they're moving. Then you have to, after some period, you have to say, where are the 4 ones we showed you earlier, and you have to point out which ones those were. And you can do that for up to 4 items, but not 4, 5 or more, roughly speaking. So that's the notion of sensory surface that I'm very often using. And we could think similarly the notion of motor surface. So motor surface here would be not just, the movement system is a surface in some abstract sense, a higher dimensional surface, in the sense you have these joint angles. There could be maybe 7 joint angles, 7-dimensional space of possible joint configurations and so on. So already somewhat higher dimensional. Again, actually inside that are constraints. You cannot actually move your joints or your muscles independently. You tend to co-vary them. And a better characterization of the motion states might be actually just the hand trajectory in space. Where are you going with your hand? That's how you control a computer mouse, for instance, very efficiently, with a spatial position of something, and not with the exact configuration of your arm or your muscle firing. And that's related to the ways you can change your postural state, the movement states. You cannot actually do arbitrary movements. You're quite constrained in the kinds of movements you can generate, quite unlike a robot. And they can be characterized by a few number of parameters. For instance, movement direction, so where in space your hand is moving, and the extent of the movement, when you typically go from rest movement and then come back to rest. And so that extent, that amplitude, those are 2 typical parameters you can look at. We'll actually later have an opportunity to look at a little bit at neurodata about that. And so representing a movement like that would be, again, spanning a space of these 2 parameters, having an activation field over that, and then there would be a peak of activation that is located over the current movement amplitude, movement direction, for instance, as a plan, current in the sense that you're next going to move like that. And such things can actually really be observed in experiments. I skipped this slide because there is actually something, this already goes a little bit further. It says, if you have peaks as representations of things that you perceive or act, and later, or maybe we'll talk about cognition, how you, maybe things that you currently work on or think about. Then there could be different kinds of situations. There could be situations where you have a single peak, even though there might be multiple objects. That would be meaning you represent, for instance, these objects as the same by some averaged peak. You could have maybe 2 peaks, or that's what I'm saying. There could be maybe a limited number, 3 or 4. Here it would be 2. You would perhaps simultaneously see these 2 motions, or you could have a selection decision where you're seeing 1 peak, even though in the stimulus there might be another peak, but you're not seeing that. You're only seeing that motion. And that will be one of those peaks becomes super threshold and the other not. And we'll see that we can concretely work with that. That's what kind of states we'll be representing in the fields, and we'll be operating with such states and look at when, under which conditions, which of those comes about. The motor system, we don't tend to have that, because in the motor system, we have usually just 1 motion plan, and we have 1 limb, and the limb is not going to split into 2 and so on. It's a little bit different. But I'll show you the next example in a moment that illustrates that idea. Actually makes that a little bit clear what that means, because you can have multiple motion plans, but not realize them. So in summary, these are the kinds of fields we'll be looking at. So there's always this dimension, and then there is the activation, that is something like information about that content, or you could also say maybe the certainty with which I am going to do something, or certainty I have about a perceptual event. I'm saying certainty because that would be not necessarily a frequentist approach. It would be perhaps a belief I have, but you could also think sometimes it could reflect really the probability of a stimulus. So that's also a greater dimension, but has slightly different operational meaning. Could also depend on really on physical properties when you have rate code. But along that other dimension, there will be the metric contents of your percept or your motor plan, or ultimately your cognitive plan. Right? So peaks have that feature that they have both activation, positive, meaning there is something, but also are localized, and that specifies a value along these dimensions. Why, if you have no positive activation, so no peak, that means also two things. So there is no value specified. It's not localized, but it also represents that you are not, you don't have certainty, you don't have a state. So it would be much more problematic to have an activation field that is homogeneous but on, it's activated. We'll come to that. It's only in special cases will that actually play a role. It will not typically occur. Now, we'll be interested in time courses of such things, right? The very natural idea would be to say, well, maybe I'm sitting there at rest, I have nothing, and then I start to decide to do something or to perceive something when an input comes in. So here, for instance, at this moment in time, maybe some input arises. I say specific input because it's localized around a particular region. And then from that, maybe a peak forms, and we'll be interested in how that happens by neurodynamics. This figure already hints that it's maybe not always a spin, maybe there is already some structure in your representation before that happens. We call it a pre-shape, because before some event, there was already some structure in the field. That's very, very common. So the idea that it will be just tabula rasa, you're not thinking of anything, that would be very exceptional. You're always coming from somewhere, from some previous percept or previous state, or from something that you learned, and building a peak of activation on that basis. Just want to jump right into something that's actually quite complex, but I just want to do that to make it very concrete. So this is actually neural recordings from a group, Paul Zizek in John Galaska's group some decades ago. And this is actually using this population code idea. So these are not neurons, these are some constructions that I'll explain later in the course, where from many neurons you can estimate how strongly these neurons vote for particular things. And here vote, for instance, for one of two targets. This is a monkey making a joystick answer, and the monkey either goes toward the filled target or toward the open target. They are spatially arranged such that one is a movement up, the other is a movement down. And the monkey gets different kind of stimuli. So for instance, here in this trial, gets these stimuli that tell it that it's going to be these two targets. There are also other possible spatial arrangement of these targets. And then at this moment in time, gets this kind of stimuli that tells the monkey it is the solid one that you're going to act out on. So here will be the top one. And then this tells the monkey you can go now. So these are different moments in time. And you see here time series of neural activation. The color code represents how strong these neurons are firing. And again, it's not individual neurons. They're sort of smeared out by some technique that I'm explaining only later. The significant thing I want to show you is that you're seeing for peaks of activation, you're really in these neural populations very directly. So you can see, for instance, here, this is the rostral premotor cortex. You can see that there is, when the monkey learns about these possible movements, there's some activation that corresponds in a way that the coding has been figured out to these two options. So there's some firing here and some firing there. And then when the monkey is told which of those is the right one, you see that after a little delay, there is a clear decision. So this here, it really selects this one, and this one is suppressed. You see the blue is very low levels of activation. It really suppresses the other option. And when the go signal comes, you see then this peak grows even further, and then ultimately dies out, and there's nothing here. The other one actually recovers from inhibition, as you see here. And in other areas, for instance, in motor cortex, you see nothing happens when you present these two choices, but then you see that actually more happens during the movement. There's some special neural technique here that it's always the same or let's say these neurons are temporarily aligned in different ways. Well, let's maybe not go too deep into that. To understand that plot more precisely, you need to know more. But could maybe get a feeling that they are really peaks. They don't look like these exact peaks that we will use in the model. And the spatial shape might be a little bit more complex, and they arise and disappear. And there could be multiple peaks, and then you can also have selection of one peak. And there are also cases where you see averaging. In fact, I'll show you later exactly the same kind of situation where the monkey makes an averaging estimate of a movement time. So there will be a module where we go more deeper into that. That's sort of the motivation for what we'll do now. Now we will look at the dynamics of neural fields generating these time courses. If you have any question up to now, this is a good moment to ask it in the chat. So what we'll now try to do is try to understand how neural dynamics of the kind we discussed could give rise to time courses like that, and it could give rise to peaks forming to express some state, and maybe peaks making selection decisions about which state and so on. And so we'll be going through that for, I think, 4 lectures at least, for different aspects. So today I'll look at the basic mechanisms, and I'll look more deeply into the detection mechanism. So the notion of these fields is, again, activation over a dimension. We'll not think about now how it came about. We'll just take for granted that that field gets inputs, like this dashed line here, that are functions of that dimension. So somehow from the sensor surface or from wherever it comes, they can get inputs like that. And so every location in the field is like the dynamics of individual activation variables we looked at so far, but there will be couplings among these variables, and the couplings will be now strictly a function of how far these variables are from each other in the field dimension. So variables that are close to each other will be coupled excitatorily, like the self-excitation that we looked at for individual activation variables, and that sort of stabilizes activation patterns from decay, right? If your neighbors excite you and you're all excited, they will tend to excite each other, keep each other firing. And this is, of course, based on the fact that the interaction is always mediated by the sigmoid function. So on the activated field sides can excite the neighbors, right? If you're not activated, if you're below 0, you have no influence on neighboring sides. That's why places where there's positive activation, those will tend to excite the neighbors. And then all other field locations, so when they're far enough from each other, certainly, tend to inhibit each other, like in this 2-neuron case when they're coupled competitively, so that a peak like this here can actually have a negative influence on activation here at other locations. And that here, for instance, this instance leads to suppression. So even though there's input, the field doesn't really make it above 0 here. And because it doesn't make it above 0, it cannot conversely inhibit this location. So it breaks the symmetry, just like for the 2-neuron example. Now that would be for a whole field. So the coupling strength between field sides can be characterized by a kernel. This would be the kernel. And the kernel says that if you look at different distances between field sides, then for short distances, the influence, it's actually reciprocal, both on x and x prime. The mutual influence will be positive. They will excite each other. And if you go far enough, it's negative. Here, this being a negative coupling coefficient. Violates Dale's law, as you know from last lecture, but we'll come to that later. We'll fix that. That's just an approximation. This is the pattern of active interaction within a population like that, within a field. I call that population, that we call local excitation, global inhibition. See, strictly speaking, the inhibition actually goes all the way through, and here you simply have more excitation than inhibition. So this would be the case where the inhibition is constant across the entire field. Everyone inhibits everyone else at the same strength. It can be also cases where inhibition is modulated. So if you move far enough, there is no inhibition left. So that's the basic idea of field dynamics. Here are the equations, and I show them just to point out that they are not so different from what we studied with the individual neurons. So here we have the rate of change of activation. It now doesn't have an index. It has a depends on the whole function. It's on a whole dimension. So x is like a continuous index, and that will be what spans that dimension and time with a tau here on the left. And then we have the minus u term, same x, right? The negative resting level here. And then the input, which is now potentially different locations. We call it therefore a function of x. So we'll generally ask that function to be smooth, and we'll check when we talk about localized input, it will be the idea that only in certain regions of x will there be positive activation. Everywhere else it will be 0. But theoretically it could be any function, but the meaningful ones are the ones that have some kind of localized structure. And now here we have an integral. For those who are not so mathematically inclined, this always may be a bit shocking. It's really just a sum for continuously many variables. So we're summing over all field locations x. We give that x a different name, x prime, just to distinguish it from the x we're looking at here on the left. And so we're summing over all field locations, and every field location contributes when it is with this sigmoid activation. So only when the activation is sufficiently positive does this sigmoid return a non-zero value. That's the sigmoid we typically use. Actually, the threshold is 0 for us usually. So it's a single parameter beta that tells us how steep that is. I have a plot of that in a moment, I believe. No, maybe I don't. And the way it contributes is determined here by this connectivity kernel. So this W is that function that we looked at. So when the field side we're looking at, x is close to the x prime we're summing over, this is a positive function. So here this would be in this regime, that will be a Gaussian kernel that is positive when these are closer than some sigma here. And you see that that sigma and that sigma are different. That's why in the book we're forced to use call this G. Too bad. Although you could say it has an index, right? So I don't know. Actually, the index is wrong, should be E. An error on this slide. I have used this so many times, no noticed this mistake, sorry. So that will be excitatory part, and then when they are far enough from each other, it will be just this number, which will be a negative number, that will be the inhibitory part. So that's all there is in this equation. We call this the Amari equation because a Japanese mathematician whose name is Amari, he's very famous. He actually analyzed the mathematics of this, characterized the different attractor states, the bifurcations that we're using. It goes back to, his paper was published in '77, so it's a long time ago. That was based at that time on this anatomical motivation for fields. I'm saying it's a good description of cortical surfaces. It goes back to a group people, including Wilson, Cowan, Ehrmantraut, a couple of people who did this kind of work. There is in here the idea of convolution, and I'm not sure how to explain that. I think if we just sum, if you take this formula and just take it as a sum, maybe it's intuitive. Strictly speaking, this is a convolution for those who know this sort of thing. So what you do is you integrate over the variable, over this function, and the kernel is sort of shifted around, and that's sort of a picture for that. I think I want to skip that. This slide is also an explanation in the book chapter I gave you, and it takes a little thinking through that. And maybe you will be worthwhile maybe for you to do that. I'm not making you learn the mathematics, but for those who have a chance to understand that, it would be useful to think through that once. So we'll be going to the website in a moment to use the simulator. Do that right away. Here, I think I've shown you that webpage before, right? I hope so. dynamicalfieldtheory.org. Look here, right? A very simple website. The link is also on the course web page. That has a lot of resources. It has a simulator right here. You can actually, by dragging, there's some explanation here how to do it. Play with the simulator. I'm not using this one because it's a little bit too easy to get lost in this one. There's also a way to boost the whole field. It's really fun. And you can select different parameter values. The blue is the kernel. You can see this is the kernel we're looking at. You can also make a kernel that is more localized, or a kernel that is combines multiple features. Yeah, that's very fun, but we're not using that. We're using a simulator that you find here under live simulators, which we saw that when we used the two neuron simulator. There's the so-called one-layer simulator, which is a cleaner version of what I just showed you. So that contains a live simulation running here in the rate depends on your computer. No, this is actually web-based. Probably still depends on computer, I'm not sure. It's web-based. So the blue thing is your field. There's some wobbling here because there's noise in this equation. You can avoid this noise by changing this knob here. And you saw that behind the blue is the green, and the green is input. And we also added the resting level. So it's a resting level plus input. This resting level is at -5. There's a slider here for the resting level. Where is it? Here, resting level -5. I can change that, right? And so the no input plus resting. So U equals H. U being at resting level is what you currently see. That's why the blue is on top of the green. Let's just distinguish that a little bit. The red line is the sigma applied to the blue. So it's currently all 0 because there's no activation above 0. Here at the bottom, and then there are inputs. There are 3 inputs. You can change their position and their width. They're Gaussian inputs. And so here, see, this is, I think, the input string. Nothing interesting happens so far because this is only the -2 term. So for instance, here when I'm making the input positive, then you see the sigma return something positive, but the blue is still on top of the green because this is now the field without interaction, only follows the input. And you can see the time delay sort of just tracks that. And other inputs are here, and there's another input here, and you can actually do things like move the input the position, and there is also this width you can make the input by. Yeah, no, just take that as well. Now here you can turn on some interactions. I'm going to take this one, but you can take other ones. So here at the bottom you see the interaction kernel that is currently implemented in the field, and this is centered around 0. So here would be 0. So this is the distance in feature space. That's the space X. We call that feature space here. And this is the distant feature space. So this would be around the X. And then we have a global inhibition. You can control that here. See, this would be shifting that up or down. And we have the size of this local excitation. You can also change that here. There's also the possibility to have some local inhibition. So that this is like an inverted Gauss. So there's a little bit, if I turn this off, you would see that it's just an inverted Gauss function. Okay, let's go back to this kernel. And now I wanted to demonstrate to you the core instabilities of this kind of model. Those are really important for the whole field, so for the whole of the course. So let's first look at the detection instability. Here I'm adding some input, and you see the system just tracks that input. And then at some point, very close here, again, instability. I didn't even touch this. Yeah, so the noise puts the system actually above the instability. You see, it's not quite 0, but the noise was enough to create some super threshold values. We have a pretty steep sigmoid in this simulator, so it comes through that quite. And you see the steepness here from the slopes here on the side. So it created a peak. You see now there is more activation than input. That comes from self-excitation. Essentially everything here, that super threshold where this red is, contributes to that integral with this weight. And because of that, it creates this positive peak. And then everything else is suppressed below resting level because this peak contributes to the integral with the kernel being here in the inhibitory regime everywhere else and suppresses the field everywhere else. So it's actually an interesting subtle point that you see I made the input quite narrow by making the width narrow. The peak narrows a little bit, but the peak's width is actually ultimately, I can make this a little larger. Ultimately, the peak is determined more. The interaction really contributes strongly to how the peak is shaped. This is actually no longer right because now the interpolation of this the discrete sampling of the field is no longer correctly reflected. So let's go back to original values and to 20.5. No, 5 is the standard default value. It's good the same. Okay, so so that's a instability as I go here through. At this point, I go through instability. What becomes unstable here is that below threshold solution, the green one essentially. Blue equals the green one. That's the below threshold solution, the one where interaction is neglected, and no red line is there, no interaction. That becomes unstable, and it means it's no longer there. The system switches to that other stable state, but that other stable state didn't arise at that very parameter value. For instance, if I lower the input like to this, you see now it's below 0 here, and I still have that peak, still stable. See, I'm adding noise, but it's still stable. And you can see that it's bistable, that there are two possible attractors here by resetting. When you press this button, it goes back to resting level. And see now from resting level, it stays here at that level. So there are two stable states, two attractors here, the subthreshold one, this one, and the one above that I just got to. I can get to that by increasing input and then going back to the value I just had. And then I'm in that other attractor. So it's really bistable in this regime. That's sort of the demonstration in a sense of the fact that what I saw was an actual instability. You can also mathematically, of course, establish that. And this fact that noise has such a strong effect at that point is maybe a hint at that being instability. So it's the subthreshold states that becomes unstable at that instability. We call that ejection instability, just like for the individual neurons. You know, in the sense that the field has a suprathreshold activation once you go beyond it, so it detects that there is significant input, whatever the input means to that field. And what I'm demonstrating here is that is a stabilized state. That is, once you've made that decision, you can weaken the input, and you can still stay with that decision, stabilize that decision. That's the core idea. If you, you know, it might not be stable all the way. That is, if you lower the input enough, at some point you lose that peak. That's another instability. We call that the reverse detection instability. I'll go through that again. Somewhere here, you lose that peak that is now, you know, that it's bistable. So subthreshold and suprathreshold is stable. But then the suprathreshold one becomes unstable somewhere around here. For instance, here, maybe not twice yet, just a little lower. Right here. Okay. Yeah, slow transit, and now it decays. So the suprathreshold, the peak state becomes unstable at sufficiently low localized input, and then you're now monostable in this state. So that's the detection. I'll elaborate more on that just in a moment after I've done those simulations. Before I go there, I wanted to demonstrate a few other things that are quite cool about that. First of all, let's first do selection. So here I'll make the peak again like that, and then I induce an input at some other location. Same input, approximately even a little bit more input. And the peak here stays, and there is no peak here. This is sort of like the two neurons that were coupled inhibitorily. Only one of them can be on. If one is on, the other is off. It comes from the fact that suprathreshold activation here, the red bar being non-zero, contributes to interaction here and contributes this inhibitory value. So it suppresses activation here. So this activation that by itself would be enough to induce a peak is now suppressed. And because it's suppressed, there is no red line here, no superficial activation, so it cannot conversely suppress this location. That's how you break the symmetry and make this stable. And it's really only because of this peak that you don't get a response. I can demonstrate by going through the reverse detection instability here. By taking the input away, then you see the peak is being formed here on the right. Selects this state, and if I now add that input, it will stay here and doesn't go here. So again, it's actually bistable. It could have selected either of those. It just depends on the history, which one it activates first, and then it will stay there. That is actually an interesting feature of selection. So it selects local maxima of input in a way, right? So it's not a big time selection, it's a simple selection, but you could think that neural networks very often are used to make such decisions. So when neural networks are used to make classification decisions, they're essentially selecting one label across many possible labels. And a couple labels might seriously compete for selection, and then the field makes, or the neural networks makes a selection decision. Many neural networks are operated in a way where it's actually not the network itself makes the decision, it's somehow a readout. You're looking where is the location with maximal activation. You call that argmax when you operate on it on a computer. There can be sometimes neural networks which actually use literally this mechanism where at the output level the neurons compete with each other and then only one of them can win. Sometimes called winner takes all, even though winner takes all is often sometimes implemented. Is often implemented also algorithmically, just looking where the maximum is. Now, so this is sort of a process implementation of winner takes all solution. So the general principle is actually something about temporal ordering. So here in the simulator, the temporal order is sort of trivial because I can only move one button at a time. So when I first induce this, let's say, go back and I first induce, I push one button up, this one wins, then I push the other button up, and this one is second. If I had started the other way around, for instance, I started with a second button first and the first button second, then it's going to take this one. And so that's kind of trivia. I had time structure in the stimulus. If I had, I can actually demonstrate that here in some ingenious way. Let's say I have two inputs that are actually not enough to make an input here, and say this input is a little bit more than that input is. You see this number is a little bit more, it's a little bit closer than that, and now I can just push up the whole thing. Actually, maybe I should have moved it more decisively. Let's move the whole thing up, and then it will select this left one, and this left one has a little bit more input than that one. And so you think, well, that's maybe a more natural thing. The one with more input wins, not the one that comes first. It's actually, these are connected, because what happens is when you have more input, you are reaching threshold faster. That's really just an exponential function that you're catching on a steeper part, because the attractor is further away. You're catching it on a steeper part. It will cover the same distance in a shorter time than if the attractor is closer. And that means that a competitive advantage in terms of input strength translates into a time advantage, and that actually makes that disambiguates these two decisions, that makes bias resistant towards selecting the stronger one. There was one more from dynamic. Just forgot that. Okay, so that's selection. And now, surreptitiously, I already showed you the detection and selection from boost, because what I did here was a more extreme version of what I do now. I'll just add now very small inputs. I have here two small inputs, maybe the third one. I have to change the width so everything is symmetrical. Make it also 5. And now let's do that just with it's for fun. Perfectly aligned in space. I wonder if that was well. I'll try to do that again. Never quite symmetrical. It should be at 75, I guess. Yeah. So now I have three inputs at three locations that are equidistant, all the same width, all very small input strength. You don't see that at all, right? It's something here, hard to see. It's very small. And I can do the same I did for these larger inputs, that is, I just boost this enough so that the sigmoid has a chance to intervene, and you get a peak. And you get a peak, you see it's a little bit almost, see the green is almost above zero here and here, but this one won. And so there's several things remarkable about that. You were able, the peak is intact peak, looks pretty much like a regular peak when it's induced by localized input. But it really comes from amplifying just a very small difference, right? A very just above zero, amplified by this homogeneous input, and that makes a full peak. But the peak's shape is largely driven just by the interaction, right? This is all lifted up by self-excitation, and then it suppresses the field everywhere else. So you can amplify very small differences into a full peak by the interaction. Now that's one distinguishing feature of these fields compared to the way many other neural networks are used. And the other thing about that is visible if I do this several times. I'm always resetting the field now to resting level. And unless I have some clever bias in here, it should actually sometimes select one location and sometimes select another location. And with some luck, I'm going to get all of those locations after enough simulations. And there's some bias in parameter values that are not shown with full resolution here. But maybe with some luck, I'll also get the rightmost one. At some point, I don't know how many times I have to do this. This one has a strong bias to the left with fields. So I have some parameter off here, no? There we go. I have the one on the right for a change. Yeah, so the other thing I would say you get is categorical responding. It generates peaks only at these three locations, never anywhere in between. Even if I add a lot of noise, I will not really get that anywhere in between. And that reflects that the homogeneity that you can get any state, that's actually an ideal limit case that is not even easy to get in a real neural network, because you have to have that the synaptic connections are really homogeneous everywhere and they feel the same. It's much easier to get the system to have some biases. And in fact, it might be even so difficult to get it symmetric across these three locations. They have to be exactly the same connectivity pattern locally, at least under these conditions. So it's not true that because we're thinking of fields and these continuous connections to sensor surfaces and motor surfaces, that these fields are not able to get categories. Categories are cheap. It's a question of how to get continua. That's actually the difficult part. So the sensory motor part, where you get continua, can make continuously many different movements or percepts, that is actually the part that you have to worry about. So together, this capacity to amplify small differences into, units of representation, as we call those peaks, that have behavioral significance, and the fact that you can easily get a categorization, those really change the nature of the learning problem. So you will see in dynamic field theory, we're using very simple learning methods, like the memory trace we'll see later is a major tool we use, which is not even Hebbian. It's like first order learning without correlation. And that can do a lot of work just because of that, because it can amplify small differences into full peaks. We also use Hebbian learning, but even if you use Hebbian learning, you see the differences that you have to generate between different choices, in a sense, can be very small, because they can be amplified by the injection into macroscopic difference. Well, let's say the classical picture of a feed-forward neural network would be to learn the synaptic patterns so that the response is, the two different patterns is really macroscopic enough to reliably tell which one is larger. And here this amplifies that difference. And here, I remember the comment I forgot to make. So you think, of course, of neural networks as not being about a decision along just the simple dimensions like that, right? A classification decision would take a complex input and then say, oh, it's a cup versus it's a bottle or something like that, or it's a cat versus a dog and so on. But the ideas are not as far from this as it seems, because what you could say is that the synaptic pattern that is developed to make these categorical decisions translates into different input strengths for the decider neurons, the classification layer at which you make the decision. So they're the neurons that are trained for cats, let's say, will have a synaptic pattern so that when you get a cat-like stimulus, these synapses match very well the pattern and give a large input to this decision neuron, while somewhere else, or the population represents dogs, let's say, the synaptic pattern isn't matching the current input so well, and therefore it returns a smaller signal to that neuron, and that amplitude difference then translates into a time difference, and that translates into a competitive advantage. So this idea that it's differences in input that translates into timing differences really applies to the kinds of neural networks that you might be more familiar with, including deep networks. Okay, so these are the detection and the selection property. Now, the working memory property is sort of emergent from that. And it's kind of interesting in that that is then where the story I just told about a deep neural network, for instance, doesn't really work. It's actually very difficult to conceive of a deep neural network that would continue to have the neurons active and thus remember the decision in the absence of an input. While this network can do that, I want to demonstrate this here by putting a peak somewhere. And what I want now is that if I remove the inputs, the peak stays. It doesn't quite do that at the input level I have here. One way to get that is to have a larger resting level, and then a large enough resting level. I don't know if this is enough. It might actually happen. Yeah, maybe this is enough. So here you have now a peak of activation at this location, even though there's no localized input, right? It's just constant. So you can't tell where that peak is supposed to be based on the input, right? Because there's no current localized input. And it's at this location only because previously it was induced at that location by some previous input, and it remembers that location. That's a model of working memory. It's working in the sense the activation would be there. If you think of activation patterns in the brain doing the thinking or behaving work, and this is a form of memory that can immediately do that kind of work. While the connectivity patterns, the synapses on that would be maybe the substrate for longer term learning, and that first needs to be translated into activation to do any work. That's what we would then call memory in the more conventional sense. So this is working memory. Like working memory, it has the weakness, if you wish, of interference. So for instance, here in this limit case, if I induce a peak just anywhere else, it will delete that working memory. You're not forgetting the working memory per se, because it would persist theoretically, except for some noise events, forever. But if you induce another working memory, it would be deleted by interference, because you can't have more than one working memory in this case. So the capacity is here limited by the fact that we have global inhibition. If I use a more realistic kernel that's here appropriately called memory, this will be a case where there is a spatial range over which this peak decays, and then I might be able to induce another working memory if I'm going far enough. For instance, here, and now I have two peaks. And you see, actually, these two peaks are repelled from each other because of the interaction kernel, and these effects are real. On later lectures I'll show you. They're actually effects like that observable for humans who try to remember metric dimensions, so it's not actually entirely wrong. So this system can do working memory, and that's based on this local excitation, global inhibition picture that sort of sets the system up for working memory. You could say the local excitation, global inhibition system makes that that you know who to keep exciting and who to suppress. That is, only locations that are close you excite, and those that are far you suppress, and therefore localized peaks are the kinds of things you can remember. So it's very specialized kind of memory. It doesn't memorize just any complex pattern of activities, only these localized peaks. It's also sometimes called localist thinking, because it's the pattern of connectivity is arranged such that there will be a selection of sites in the field where activation is structured. Those of you who know, for instance, Hopfield networks might know that you can build attractor states that are much more complex, and that is true, and that's actually used as a model of memory in other contexts. But that would be memories that you have really learned, where you have to learn the synapses. The synaptic connections in Hopfield network are such that they know exactly which pattern to stabilize, which neuron is supposed to excite which, and which neuron is supposed to inhibit which. And so you can only do that for something that's deeply learned. While working memory, supposedly you could memorize a color you never saw before, as long as you have some color representation. There's a question from Simon about working memory capacity limits. Yes, the capacity limits actually are very intuitive. I showed you the extreme capacity limit of just one if I have global inhibition, and the simulator isn't made for tuning that very well. But generally they arise because as you add peaks, so as you add here the suprathreshold activations for whatever kernel you have, there will be more inhibition in the field. These negative things will be projected all along the field, and therefore there's a natural tendency of these fields to have a capacity limit. So if you don't change something, you cannot keep adding peaks. At some point, the accumulated inhibition will start to prevent you from building new peaks. That the capacity limit is something like 4 plus minus something is not necessarily explained by these fields. We can make fields have 12 peaks, or there's some question of how much room we have in the field, given how broad the kernels are. This is what you see in this trivial simulation. But there's also really the accumulative effect of multiple peaks when the inhibitory region overlap, that they make it difficult. And so we can't predict the exact number, but we can certainly predict that as a universal feature. And because working memory is actually the basis for everything, every mental operation. There's very few operations are done really while sensory stimulation comes in. That's a very universal bottleneck that we have. Yeah, so this is a model of working memory only along one feature dimension, so it's not very trivial. We actually deal with conjunctive situations, and I will be talking about that in the second part of the talk. Of the course, we'll talk about multiple features and binding across features, and how you can use binding to account for instance, change detection when you represent perceptual objects of the feature dimensions. This account of working memory is also neuronally realistic, and I'll have a little module about that. Even though there is some debate about something called resource allocations on, but that's sort of misleading. It's a debate. Both is true. So this is basically mechanism, but you can also actually allocate resources. For instance, you can make the resting level a little higher here and lower there. So I also want to point out that this is just a very trivial way of making working memory. You can also get into this dynamic regime where working memory exists by changing the kernels, right? Good. This is about as much as I wanted to do on this website. And I want to go back to slides and summarize what you just saw. So what you saw were that we're talking about fundamentally two solutions: the input-driven subthreshold solutions, so that are only present in the presence of input, versus these peak solutions. We call them self-stabilized or suprathreshold solutions. So those are the field versions of the on or off state of the individual neurons, right? That's all that means. And so the detection instability is what takes you from the subthreshold to the peak solution. And it's the subthreshold that becomes unstable, sorry. And what takes you backwards when you lose a peak, that's the reverse detection instability. So that's the same thing you saw in the individual neurons. Then I showed you the property of selection. I think I forgot to show you the selection instability, which occurs when you're, let me actually take the really quickly back there. If I go here and load the kernel and this one, then the selection is, selection. I put up this peak, and the instability is that I can actually make this location win and turn off that if I make the input here large enough, and if I then return to the same value, now it will be stuck in this one, right? And I can switch it back, and then return to the same values. Yeah, so in other words, this bistable regime where you have one selection selected over another has limits, and that's where we have what we sometimes call the selection instability. And that is not just true for two choices, you can do that for many choices. And then there is working memory, which comes with its instability. The instability in the working memory consists of the reverse detection instability disappearing. So if you have an input, some change of parameter that makes that the reverse detection instability happens, at 0 or less than 0 input, then you will have effectively gone from a field that has working memory, that does not have working memory, to a field that has working memory. And the last thing I showed you is that you can get the detection instability even responds to non-localized input, to just homogeneous or boost input. Nothing different mathematically about it. And that leads to this categorical behavior and sort of a form of amplification of small inputs. You saw in some of these simulations that noise can then really make a difference, that you can get different outcomes from the neural dynamics for, just by chance, when you repeat the experiment. So that's how we get stochasticity in these systems. And you think, noise is the obvious source for stochasticity. We know in the nervous system there's lots of noise, actually. It's an intrinsic feature of neurons. It's on purpose in some sense. The distribution of stochasticity is actually very reproducible. I can give a long lecture about that. And the critical thing is that the noise has this effect only near instabilities. It is near impossible to take a field like that and make it suddenly jump over here to this one. Actually, you have a level of noise at which the field becomes unstructured. I can't even put the slider so high here. For that to happen, it will not happen. Let's say if I make everything a little bit weaker, these inputs, maybe I can get somewhere that you can see the destructuring of the field. So you see the sigmoid is now just random here, and then sometimes it can go here or there, but now it's no longer really showing coherent states. So I cannot get into a regime in which there is a stable peak, let's say like this, and then by noise I can really make it switch from a whole peak like that to this. But I can get that very easily if I go through an instability. So if I, for instance, here, delete that, and now I push it through, and then I can get the system to make a stochastic decision. I can even just use the reset for that. Now these are not actually biased, so I will sometimes, it will be very strongly biased to one. But here's another instance now. Makes a stochastic decision. So it makes a stochastic decision only near instabilities. So there's a question of, by Simon again, it would be, such a boost would occur. Yes, so so there are, the boost is rather, normally, yes, the boost is really means that you have essentially just broad input. That is when you, so localized input really reflects that you have sort of information about the state you're operating on. This will be quite important in cognition, that you know who to boost. And so that is typically the thing that is sparse in the nervous system. And I was hinting why it's sparse, because we have this non-synesthesia principle, right? That there are only a few paths through the architecture that create localized inputs, because those know about what to represent. But you can also have inputs that are broad. For instance, that really just means that, neurally speaking, that the dendritic, the axons make connections, in a large sector of a particular representation, and that is not uncommon in the nervous system. And then they don't have to be exactly homogeneous, right? That's always an idealization, but broader than any peak or any of the, so broad enough so that multiple selection decisions would be within the width of these inputs. And that's very common. And in fact, that is, so this question is, do you take neuroanatomy for that, or if you take neural accounts for phenomena? But let's say certainly a mechanism very frequently invoked in connections models. And there's ample substrate for that neurally, even though we don't know exactly which neural substrate serves which of those functions. So Simon is asking, if you can directly map that onto sensory inputs. Now, sensory inputs, it would not be so common that you have like a global input that comes from the sensory surface. These sort of inputs would more likely come from somewhere else in the architecture, and that's where we will be looking. Because these sensory input paths are much more fixed, and they actually have a lot of gain control kind of mechanisms, so that they don't. So if, for instance, if you make the whole room brighter, then there's actually immediately a way of turning down the gains to get back into the working range of your neurons. No, so the idea is not that these boosts would really directly come from sensory surface. They would be more generated internally, for instance, from you making a decision. For instance, you can keep your options open, and at some point you make the decision to go when you're certain, and that would be done internally by sending a boost to a certain population that makes the decision. But that's not coming from stimulus, it's coming from something like cognitive control, like a system that, for instance, has a timer running and after some time makes a decision. I'll actually show you something like that next lecture in the so-called time movement initiation paradigm, where you make a decision at a given point in time, and that can be triggered by a metronome, but it's not. It's ultimately internal signal. It can be entrained to a metronome, but it comes from a different source than the sensory source that you're using for the decision. Good, great. I appreciate these questions because it really helps to discuss it a little bit. Okay, back to these slides. I think I took a little more time than I thought, and maybe wonder if I'm going to do the detection module, which is not so important, perhaps. So I showed this graph before. Just I wanted to connect back to what you learned in the first neurodynamics lecture 2 weeks ago. So there we talked about one neuron and another neuron, right? And these were self-excitatory, and then under some conditions they were mutually inhibitory. And so you see, if you think of these neurons just representing local regions, then the self-excitation was some kind of effective, approximate description or phonological description of what the field would do, with different locations within that region would excite each other, and you could reflect, say, the whole activation in that region is then captured by that one activation variable, and that would be self-excitatory. And then the inhibition would be because these neurons in this region would be inhibitory coupled to neurons in that region and vice versa. So if I represent the whole region by individual activation variables, that would amount to a mutual inhibition between those variables. And you see in this picture that we had with the individual neurons, it's what is clear is what do those neurons stand for, right? You say this neuron 1 for one choice, that's 2 for another choice. How strongly are they inhibitory coupled? Well, you can tune that. And that's sort of conceptually weaker than really committing to a particular mapping onto the motor or the sensory domain, which fixes what a location here stands for. And therefore, you can't just say this stands for a choice, and that stands for another choice. You have to actually figure out. And the metric differences between these choices will actually determine how strongly they are inhibitory coupled, or if they're inhibitory coupled at all. And I'll present to you in the next couple of lectures some examples and evidence for metric effects for the dependence of, for instance, reaction time on the metric differences between choices that reflect that, which one can model that with individual neurons by just assuming somehow that the interaction strength is a function of distance, but it isn't. There's nothing predictive about that. Well, it's very structural and predictive in this field picture. So this may sound trivial, but the actual fact is that there are connections, neural networks sort of that embrace the same underlying framework of using activation variables to represent contents, and the connectivity determines how that content comes about, and so on. So they are not there. We're not in conflict with these kind of views, but there is a tendency, especially in the older literature, to just make such interfaces, saying here's some neurons that stand for this letter, here's some neurons that stand for some other letter. As soon as you do that, then that is quite unconstrained, right? You would want to embed such representations in a plausible sensory path and motor path to make sense of that. In more modern connections neural networks, that happens in that sense that, for instance, in deep networks, that the connectivity was learned so that neurons do stand for this particular letter, because now they really collect the activity, the stimulus activity from the retinal array, and it is metrically correctly tuned so that it really answers when that letter is present somewhere on the sensory surface. And some of these more modern models are actually used to link up to psychophysics. It's not maybe it's not entirely, it's a bit too unconstrained, a lot of that modeling, but it's conceptually more consistent with this than just taking individual neurons and saying they stand for something. Okay. So I wonder if I should do the detection instability. I can maybe do that real quick. It doesn't have to elaborate that very deeply. So my plan is actually now to take you in the next 2 or 3 lectures, take you through these instabilities one by one and link the picture of these instabilities up to psychophysical evidence. And so to say, how do you see that something like that is a good description of how we make, let's say, sensory motor decisions, at least in simple forms of cognition? For the detection, this is sort of the most elementary, right? Detection is really right at the sensory surface. So here's again a caricature. This plot is never so easy to understand. So what I'm talking about is that there might be a level of input. The localized input here is this gray line, at which there is a unique response, only one subthreshold hill, as I call this here. And there's another level of input, a very large input, where there's a unique response that's just a peak, self-excited peak. But there are intermediate levels of input where you can have 2 different possible responses. For instance, at this level, you could have the subthreshold response, but you could also have the self-excited peak if you're coming from this end, if you already had a self-excited peak. And at this level of input, a little bit more, you would have still 2 levels of input. That is a subthreshold level that is maybe close to instability now and would become unstable just with a little bit more input, and the self-excited peak that we were just talking about. So this is this monostable, bistable, monostable transition with the detection instability would be happening somewhere here, and the reverse detection instability would happen somewhere there. That's what I'm talking about. So at the face of it, if you look at that, the work the detection instability does is stabilizing on-off decisions, right? So here's an simulation again from resting level. You apply some stimulus, and then it goes to the new stable state. See here is the threshold. You want to take 0 as a threshold. This is a steep rise because it goes through the sigmoid. It really has a transition. It doesn't fluctuate a lot around 0 here. It fluctuates around the attractor, but you're not doing any thresholding. You're just making sure that this state here, every state here above, let's say 0, could impinge on some low-level state. I overlooked a question that was there. If I could repeat the memory instability, yes, I can. Let's do that because that's more important than getting through the program. So I'm going back to parameter values that are more reasonable here. But let me just reload that web page because I did so many changes. So the memory instability I didn't really explain well. Let's take, I always like this because it's simpler, this parameter set. So to probe whether I have a memory, what I have to do is work memory. I induce a peak and then remove the localized input, and I lose the peak, right? And so currently this system doesn't have any working memory because when I take the local input away, it always decays. And that is because as I lower the input, I go through the reverse detection instability. You see somewhere here, I'm losing that peak around here. That's the reverse detection instability that happens. And it happens at a non-zero localized input. See, it's still a little bit input, actually, it still hasn't gone through that. I do like this now. I lose now, so it's not close. But there's still some non-zero localized input, right? So I get, so the field, yeah, so the field has, in terms of detection instability, as I was just saying, has a monostable regime here, where it makes just a subthreshold solution that is a little bit distorted. Then it has a bistable regime, if I go a little bit higher, where it has this off and the on state, both in this regime, both is possible, and then has a monostable regime up there. Now the working memory instability is where that second bifurcation is gone, so the system is bistable all the way down to 0 activation. So for instance, one way I can get it here in this, I can play with these parameters to get it, but a simple way is to boost the whole field. And if I boost it, then it might happen that now I have no longer the reverse detection instability. As I go down here, I can go all the way to 0. I'm not sure this is actually true. Maybe it isn't. I can sort of see that live. If I boost this a little bit more, then the detection instability will occur at smaller and smaller amplitudes. So, not sure. Not there. Yeah, just barely, but very close. So now I'm at 0 amplitude, and it's still bistable, but is the self-stabilized peak is still stable, and there's also the offstate. So we said, this is also stable. So it's still bistable at that level, and it will still go through the detection instability. So if I go up here, it becomes more stable if I have enough input, but it remains bistable at the lower end. And that is qualitatively different from the case where it becomes monostable at the lower end. And that transition is called memory instability, and it's brought about here by the resting level. So if I make the resting level lower again, then the regime becomes monostable here. This is what you see now. This is sort of the trivial case, right? It can be made more complex by having other kind of interaction points. So this was actually a good illustration of the problem that we're confronting detection instability, because we're going from one stable state becomes unstable to a new stable state. So it's not a transient, it's really going to a stable state, stays there. So if you think of, the most common way people think instead is sort of have a readout, right? Rather than say, oh, I have to, the neurons themselves make a decision to say, I have some observer function is sort of my algorithm that looks at some neural network in which stuff threshold fluctuates, and then I'm taking a threshold reading. And whenever the threshold is pierced, then I say I make the decision. And what I'm claiming is that generically, if a network like that, without any instability, goes through a threshold, it will go through a threshold many times. This would be typically a random walk. For instance, this happens in the so-called diffusion model of reaction time, for those who know these sort of things, where it will be a random walk that takes you to a boundary that is the decision boundary, where when you go through that boundary, that threshold, you make the decision. And mathematically speaking, it's actually, you can prove that around any threshold piercing, there are infinitely many around in time, infinitely many further threshold piercing. So if you make a decision, then you're quite likely to unmake it again next moment in time, make it, unmake it. So that sort of would be terrible, right? That's just isn't noticed in these models because they just take that reading and then ignore the model for the rest. But if it was really coupled to motor systems and you know, to do that, then you would make the decision and then stop and make, so arm would, you know, start moving and then stop moving and so on. So in a sense, that is the quality that that detection instability gives you. It goes into a new stable state that persists after that and doesn't depend so much on the input. And there are, it just says that in words, and there are empirical signatures of that. The most direct one would be to observe some kind of hysteresis. And so, for instance, I don't want to say this, I said that before, hysteresis. And so, for instance, you could say, you know, could I slowly increase the stimulus and make you see something and then remove it again? And would you then maybe, you know, stay with the decision that you see it? And these things are actually very commonly observed in psychophysics. They were known to Helmholtz and the original psychophysicists. They actually introduced special tricks to get rid of it by coming from top and from bottom, so some kind of staircase procedure. And a lot of people thought that it was maybe not a deep thing. It was maybe more something called response bias. That is when the stimulus is very unclear, you're quite uncertain about your perceptual decision, then you might just keep saying what you just said. So when you show the stimulus in increasing order of intensity or decreasing, that you would tend to some kind of inertia and responding, you would just say the same again until you're really sure it's different. But there are more modern techniques that minimize that and that provide good evidence. So I'm involved in some of that work, so I just wanted to briefly highlight like that. So one really cool one is using apparent motion, so-called generalized apparent motion. Apparent motion, I think you all know, is like what TV works, even this computer works this way, right? It's still images that are shown at a certain frequency and they allow for a certain level of change. And then you will see smooth movement, even though it's actually just a sequence of still images, right? And so that's, you know, all the media use that all the time. And so in the laboratory, the minimal version of that would be to show this kind of display, though there is a brighter and a less bright square, and then the next frame you just switch the brightness. So in the next frame, the bright one is on the right and the less bright one is on the left. And if you do that at the right frequency and with the right levels, then you see the bright one switch back and forth. You can do that periodically. So the classical apparent motion would be the bright and there is nothing here. So the background and the spot have the same luminance levels or contrast levels. So you would have the same background gray here. And then you see very clearly the white one go back and forth. But in so-called generalized apparent motion, you have some contrast at that, you know, location where you come from or that you go to, and you switch it around. So the luminance levels are not background, but they're above background on both, and you're just switching which one is closer to background. And that is cool because that can create a onset of motion with very little perceptual uncertainty. Now, when you the other one, what you do is you make it very fast and make it very slow, and then when it's very slow, you see it maybe more like a sequence and not really like good motion. And when you're very fast, it's ultimately just blurry and just some flickering. But here you can keep this space and time structure invariant. You have the same temporal frequency and same spatial distance, and all you change is the relative to background luminance change, BLRC. So I don't have to explain it exactly, but it's really just the luminance level. So you make the distance, the change here, larger compared to how far these two are from background. Very bright stuff, changing luminance versus less. And so when you do that, then, so the spatial temporal structure is the same. Then you find that for large background relative luminance contrast, you get very clear motion. And for small, you get very clear non-motion. And as you increase step by step that background luminance contrast, you see the onset of motion at higher background relative luminance contrast than if you decrease. And when you do that as a participant, you have no doubt, it's not like you have perceptual uncertainty. You really see that coming on, and actually naive observers will usually assume that something was switched, that this is a different stimulus. They don't realize it's the same at this intermediate level, that it's the same stimulus that they see moving or as non-moving just because of their prior history. So that's one of the cleanest cases of doing that. We're also using a so-called modified method of limits, where we're actually not asking people to report all the time what they see. We go through a sequence of stimuli that end at different endpoints here, and they end surprisingly. So it's all randomized, so it suddenly ends, and you just have to say what you saw last, and from that we can or you can ask different kinds of questions, and from that we can reconstruct these probabilities of switching. And here is an even more radical example. This is a paper we haven't even yet submitted. Actually, we decided to write it totally differently from the first attempt to publish this. It is the lowest level thing that you could even think of. It is just that you're just detecting some contrast. So here is a very thin object here, this gray object, and this is just a baseline condition. Forget about that. Psychophysicists have to do certain things to make this right, but we can think of just this example. So your task is to detect this kind of object, and in the study where we're coming from is that we're looking at the influence of a nearby brighter object. So what you find is that if you have a bright object here, it suppresses that probe, and you will need more contrast at this probe to see it. And it's a question of how far you are. If you're close, then it will really, in the presence of the probe, you will need much more contrast to see this than if it's far. So that's sort of a background idea for that. And now the interesting thing is that because of that, maybe I can't explain all of the details. What we can now do is we can vary in time the contrast at that probe location. And so ascending trials and descending trials. And because of some of the stuff I just showed you, we have no problems with attention or anything like that. And we get hysteresis in just the onset of seeing a little piece of contrast. It's also the object always there, and that is important for the perceptual certainty. Very robust. I mean, we've done lots of different variants of this. So whether or not you see this gray line depends on whether you increase from zero the luminance, then you need more luminance to see it than if you decrease from higher luminance. So you keep hallucinating that line once you saw it. So even the lowest level kind of decision, whether there's a little fleck of contrast, is actually hysteretic, and therefore reflects the detection theory. Yeah. Okay, so with this, I wanted to close this first foundational lecture here.